In this lesson, I'm going to be showing you how to graph sine and cosine. Now, sine and cosine are called sinusoidal functions or periodic functions. And the reason that they're called those is because they repeat themselves over a particular interval. So as you know, sine and cosine are directly related to our unit circle. And if you recall, on our unit circle, we can continue going revolution after revolution around the unit circle. And our sine and cosine values would just repeat themselves. So those coordinates around the unit circle repeat themselves over and over as we continue around the unit circle. So when we're looking at these sinusoidal or periodic graphs, there are two things that you need to pay attention to. The first is the amplitude. The amplitude of a sinusoidal graph is the distance from the x-axis up to a peak or a valley on the graph. Basically, we're looking for how tall is the graph from the midline. The period of a graph is the interval after which the graph repeats itself. So we're asking, how long does it take to do one complete wave of the graph? These will make a lot more sense once we start looking at these graphs. So we're going to start with the graph of sine. Now what I've done here is you'll see on the top, normally in our graphs, we would graph x and y. What we're going to graph in this case is we're still going to graph on the y-axis, we're going to graph sine theta, and on the x-axis, we're going to graph theta. So on the x-axis, these are theta values or angles, and on the y-axis, these are the sine values that go with each of those angles. So what I've done is I've taken some key points off of the unit circle. Now, I've specifically chosen theta values where the sine value is like a nice, easy number to work with, like 1/2. Like 0 and like 1. I haven't chosen where sine is √3/2. You're not going to need to use this table of values once you're graphing these, because you'll see that sine and cosine, you're going to learn really quickly how to quickly do a sketch of them without needing to actually go angle by angle and determine your coordinates. So this is just to sort of show you how we build this graph. So if we start at theta equals 0 on the unit circle, at 0, the sine value, or the y value, is 0. So that's my first point here. At pi by 6, the sine value is 1/2. So that would be in and around here, would be at 1/2. At pi by 2, the sine value is 1. And then we continue on from there. So at 5 pi by 6, the sine value goes back down to 1/2. At pi, the sine value is 0. And then at 7 pi by 6, it's -1/2, -1, -1/2, and 0. So you can see that this sine value goes from 0 up to 1, back down to 0, down to -1, and back up to 0. And if you continued around the unit circle beyond 2 pi, it would go back up to 1, back down to 0, and then back down to -1. And it would continue on and on and on. So when I look at this graph, I've just shown you between 0 and 2 pi. At pi, the value is 0. At pi by 2, it's 1. And at 3 pi by 2, it's -1. So these are the most important values that we're going to look at. Now, on this graph, you'll see the amplitude, which remember is how tall the graph is, the distance from the x-axis to either a peak or a valley. Now these graphs, a sine graph, will always be not symmetric, but that amplitude will be the same whether you're going up to a peak or down to a valley. If it's from the x-axis to the top is 1, then the x-axis to the bottom is also 1 on these sine graphs. So in this case, our x-axis is our midline, the amplitude would be 1. The period of this graph which remember is how long it takes before the graph would repeat itself, is 2 pi. Essentially, 1 revolution around the unit circle. So the period is going to be 2 pi. After we get to 2 pi, this graph would continue with the same pattern. The domain is that theta, remember we're working with theta, not x, theta is equal to all real numbers. And our range in this case is that we are only going from -1 up to 1, and this graph is going to oscillate between those two values. Our y-intercept is at 0, 0. And our zeros, so this means any time that the graph hits the x-axis, so remember this is also, zeros is just another word for x-intercept, are at all the multiples of pi. So at 0 pi, at 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, etc. So we can write this as pi plus pi k. This is very similar to general form that we looked at in the last unit, where k can be any integer. So there is an x-intercept at each whole multiple of pi. So this is the graph of sine. It starts at the origin, it goes up to 1, down to -1, and back to 0. If we look at the graph of cosine, it's very similar, but the starting point, or the y-intercept, is a little bit different. So again, I chose theta values from the unit circle, where the cosine value was a friendlier number to work with, so 1, 0, and half. And you'll see here that the biggest difference is that at theta equals 0, the cosine value is 1. So at the y-axis, this graph is starting at 1, but then it still goes in the same pattern. So we go to half, 0, -1/2 to -1, and then after that we start moving back up to -1/2, 0, 1/2, and 1. So this graph is essentially the same as the sine graph, it's just sort of shifted over a little bit. So again, the amplitude of this graph is 1, that's the height of the graph. The period is 2 pi, so it still takes 2 pi in order to complete one full wave. The domain is still theta is equal to all the reals, and the range is still -1 to 1. Our y-intercept is now 0, 1. And our zeros now, instead of being at intervals of pi, they're actually at intervals of pi by 2. So here, sorry, I should restate that. The first intercept is at pi by 2, but they are still spaced out by pi. So we have an intercept at pi by 2, and then at 3 pi by 2, another one would be at 5 pi by 2. So these are at multiples of pi, but they start at pi by 2, instead of with the sine graph, where they start at pi. So those are the two graphs of sine and cosine. You're going to need to refer to these. These graphs are going to be just like the graph of y equals x squared, or y equals 1 over x, or even a linear graph y equals x. These are another basic graph that you need to have in your toolkit that you need to be able to graph. Now, surprise, surprise, what we're going to do with these, just like every other graph we've done in this course, is we are going to do transformations on these graphs. So we're going to start with vertical and horizontal stretches. So, as you recall, when we're working with transformations, we have A values and B values. So in previous units, we looked at stuff like this. We looked at when you might have B value, and we've done horizontal and vertical stretches. These work the exact same way. So you'll see here the starting graph is y equals a sine b of x, or y equals a cos b of x. Again, the A value, just like in all the transformations we've done so far, represents a vertical stretch. It can also represent a reflection. So if it's negative, it's a reflection. The B value is a horizontal stretch, but always by the opposite. So it's a horizontal stretch by a factor of 1 over B. And if B is negative, then the graph will be reflected over the y-axis. So that is all the same as all of the transformations that we've done thus far in this course. Now, specifically related to these trig graphs, the A value will also tell you your amplitude. So the A value will tell you how much you're stretching vertically, which then changes the height of the graph and tells you what the amplitude is. The B value is actually going to change the period, because if you think about these wave graphs, if we have, for example, a sine graph that normally we would have from 0 to 2 pi would be the period. If we horizontally shrink this or stretch this, essentially we're shrinking this in so that it repeats itself. Maybe it repeats itself only in pi, or stretching it out so that it takes 4 pi for the period before the graph repeats itself. So we can calculate the period using the B value. And you do this using 2 pi divided by B, and we use the absolute value. We do the reflection separately, or 360 divided by B. And it's important to note that when you do a horizontal stretch, the x-intercepts will also change. And as always, just be really careful to watch for reflections. So let's start with an example. This will help it come to light a little bit. So if we start with, on this graph, I've already provided you with the basic graph y equals cosine theta. It's drawn here in black. It's already in your booklet for you. This information, the amplitude, the period, the zeros, the intercept, and then the minimum and maximum, we've talked about already. Minimum and maximum, we haven't specifically said, but obviously the minimum is the lowest y value and the highest y value. Now, question B is asking you to graph y equals 3 cos theta. Now these, you'll notice this is an A value. All of these are all A values. These are all vertical stretches. So all of these, we're just going to stretch the graph vertically. So using the graph here, if you're looking at B, this is y equals 3 cosine theta. What this means is that the amplitude is going to multiply by 3. Instead of the maximum y value here being 1, the maximum is going to be 3. A y value of 0 stays on 0. A y value of negative 1 becomes negative 3. 0 stays on 0. And a y value of 1 goes to 3. So I'm multiplying the y values by 3. That's what I'm doing in this first example. Now what this changes is the amplitude now is 3. The period is still 2 pi because we haven't changed anything horizontally. It still takes this graph 2 pi before it repeats itself. The zeros are not going to change in any of these, but the y-intercept changes and the min and the max change. They go from negative 1 to negative 3 and from positive 1 to positive 3. In question C, very similar, but now my amplitude, instead of it being 1, the A value is a half. So the y values are being multiplied by 1/2. Remember, that's the same as dividing by 2. So instead of a maximum at 1, we have a maximum at 1/2. 0 stays at 0. Instead of a minimum of negative 1, the minimum is negative 1/2. 0 stays at 0, and my maximum goes down to 1/2. So all those y values have been multiplied by 1/2. Again, the amplitude changes to 1/2, but the period and the zeros stay the same. The y-intercept, the min, and the max all change accordingly. And then finally, question D is a reflection vertically. So remember, your y values will change sign. They'll change signs. So when you have a y value of +1, it will become -1. 0 stays at 0. You'll notice that's been the case with all of these vertical stretches. -1 becomes +1. 0 stays at 0, and +1 goes to -1. So all of those y values change signs. Here, again, my amplitude would still be 1 in this case. Remember, the amplitude would not be -1 because our amplitude is always a distance. It's always the absolute value of A. Period and zeros don't change. The y-intercept, the min, and the max. The min and the max are actually the same as the original, but your y-intercept changes. So what you'll notice here, these were all vertical stretches. Only the y value changed. The x values did not. And in all of these points, or in all of these examples, what you'll notice is the points that I chose to work with were always the y values of 0 and 1. Those are the easiest ones to work with. Let's look at example 2. In example 2, it's a little bit harder to look at. This is an example of, you'll see here, these are all b values. These are all horizontal stretches. So for all of these, the x values are going to change. So if we look at, I'm going to actually draw this separately. I'm going to draw it. It's really hard to see on this graph, so I'm going to draw it as we go. So if you look at the original function, y equals sine theta, it's already drawn for you. If we look at the second one, we've got y equals sine of 2 theta. Now remember that horizontal stretches, this is horizontal because that's a b value, we always do the opposite. So for this question B, we are going to do the x values times 1/2. And the x values that I'm going to use are all the peaks, the valleys, and the zeros. So here, the x value is 0. That point's going to stay the same. At this maximum, I need to divide this in half. Now the grids didn't print very nicely here, but we can see this is 2 pi. So then this is pi by 2. So instead of pi by 2, it's going to move in halfway to be at pi by 4. This point here is going to move in, right? We're dividing by 2. So it's going to go from pi to pi by 2. This minimum is going to go from 3 pi by 2 over halfway. And then this is going to go from 2 pi into pi. You'll see what I've done here is I've ended up with a sine wave that's just been squished in. So I've moved it, I've squished it in. And you could continue doing that for all of these points. What you'll notice is a pattern here that your zeros are now at every pi by 2. So if you just drew those in and then followed the pattern of the wave, this is going to go up, down to -1, up to +1, down to -1, and so on. The best part about sinusoidal graphs is that they repeat themselves. It makes your life a lot easier because you can use the pattern of the graph to help you out. You really only need to find a few points, and then from there, you're able to just follow the pattern of the wave. Now, that is for 2 theta, sine of 2 theta. I'm just going to erase this so that I can do the next one and you can actually see what I'm doing. Remember, you can go back and look at my PDF version of the notes to see it all together. In the next one, we're essentially just doing the opposite. So here, the b value is 1/2. We're going to take our x values and multiply by 2, because we always do the opposite when it comes to horizontal stretches. So again, here the x value is 0, so it's going to stay in the same place. Here the x value is pi by 2. We're multiplying it, we're doubling it. So it's going to move over. This point is at pi. It's going to move over to pi by 2. So you can see here already the shape of this wave. And as long as you've done that correctly, you can actually use this pattern to continue. But I'm going to keep showing you. So we just moved pi to 2 pi. 3 pi by 2, notice, is 3 over. So we're going to double that. We're going to move it to here. And then we're going to continue. I'm going to run out of room. Here we go. 2 pi is going to go up to here, and that's actually all the space that I have on this graph. So that is the graph of sine of 1/2 of theta. Now, I haven't included over here, but you should continue this pattern on the other side. You would have a very similar wave. This would go down, then up to the middle, then up to +1, and back down. So once you have one side of your wave, it's really easy to sketch in the other side. So that would be the graph of sine of 1/2 of theta. Last but not least is sine of negative theta, which is our reflection. Again, I'm going to erase this just so you can see what I'm doing. In this case, I need to reflect all of my x values or change their sign. So change the sign of all the x values. So in this case, 0 stays at 0. This point here, or I guess I should start up here. This point up here is going to reflect over. This intercept here is going to reflect over. You'll see it ends up landing on this reflection, on this intercept. This is going to reflect over, and this 2 pi is going to reflect over. What you're going to notice here is that this horizontal reflection looks very much the same as a vertical reflection. It looks like the y values have just reflected, but we've actually reflected this whole side onto here, and I could reflect this side onto here. So this would reflect over like so, and you could continue with that. So if we look, that would be the reflection of sine of negative theta. If you look at your table here, you'll see that the only things that change are your period and your zeros. For your period, the period is 2 pi. In order to calculate the period, you always do 2 pi divided by b. So in this case, 2 pi divided by 2 gives us a period of pi. 2 pi divided by 1/2, if you flip and multiply, gives us a period of 4 pi. And then 2 pi divided by b in this case is just -1. I should just write this down. Remember, we use the absolute value of b, so the period doesn't change for that reflection. For your zeros, very similar. You also are just going to divide. You've got k pi. When we divide all of those by 2, we get k pi over 2. When we divide by 1/2, k pi divided by 1/2, we get 2k pi. And then for that reflection, the zeros don't change. The y-intercept, the min, and the max and the amplitude are not being affected by these horizontal stretches at all. This lesson seems really complicated at the beginning. I promise once you start working with them, they do come together a little bit. So try out the practice questions, and we will go over more examples together.